Hi everyone, let's start today's class. So the topic that we will be covering today is object-oriented programming. So what are objects? We have seen many different data types that we have defined in our previous classes. This first one, for example, is an integer number. The type of this variable value is integer. This is a float data type. This is a string. We have a list here, and this one here is a value of type dictionary. So everything in Python is an object. It is inherited from a type called object, and that object contains some basic behavior of how that data type will behave, what kind of values it has, other than the inherited type of integer and float. So what is an object? It is a type. Um, there are many types which are built in or defined as part of the Python programming language, but we can also define our own types, and that's what we will study today. So every type or every object has some data that it contains, and it could be one of these primitive data types, like integers, floats, and strings, but it can be another object or another class as well, and we will take a look at a few examples. Other than the data that it holds, it also has a set of functions or procedures which define the behavior of that object, and that's how programmers can interact with the object. So for example, this 1, 2, 3, 4, it's an instance of an integer, and its value is 1, 2, 3, 4, which means the data that it contains is a number, and the current value of that specific instance of a variable to which we assign 1, 2, 3, 4 would have this number as its data. And it also has some behavior attached to it. For example, we can add two numbers, we can print a number. All of those functions that we call for that number, they are the behavior of this object integer. This, on the other hand, is an instance of a string object in Python. So let's move on. What's really meant with by object-oriented programming in Python? So everything in Python is an object, as I said earlier, which means it has a very specific type, and the type is defined by the data it holds and the functions it has as part of its implementation, which define its behavior. So what we can do with objects, we can create new objects of a specific type. We can also manipulate them, which means we can use its behavior and its functions to interact with that. We can destroy objects. For example, if I have an integer a that has some value, and then I assign it something else as another value, the memory that was occupied by this number will be destroyed when the garbage collector runs in the background for Python. So here's an example. So objects are a way to abstract data and behavior behind a name of a specific object or a class. For example, all of these are instances of a class called car. They look different. They behave a little bit differently than each other. Each of them have for example, a different top speed, maybe a different set of a number of gears. Some of them might be manual, some might be automatic. So that's all part of either the data or the behavior of that car. Here we have an example. Car may have a specific color. It would have a current speed when it's running. It would have a specific fuel level. But then how do we interact with it? We can start it. We can speed it up, and we can stop it. So all of these, this is the data, and this is the behavior of the car, and this car is an object that, let's say, we have defined. So the internal representation is all of the data elements that are part of it, and the interface for interacting with the object are all of the functions or methods that we define within the class. And we will take a look at an example, couple of examples for that. So list, we have used it in many examples in our previous lectures. How is it implemented internally? We don't know. And we don't know because of abstraction. We, as the users of the language Python, we define a list and we just interact with it by assigning it some values, by slicing it, by adding two lists, for example, or by using these functions of min, max, delete, the length of the list. We can also append to the list. We can extend it, remove elements from it, reverse it, or sort it. So all of these are ways to interact with the class. And during this interaction, what we are dealing with or what we are using is all of the data that is stored in the class. And the way it is implemented internally is probably using a linked list. So all we see are these numbers 1, 2, 3, and 4. But internally, what happens is for each of the index, there is a pointer to the next one. And this one has a pointer to the next element. And that's how internally Python may be implementing the list class. When we remove a certain element, for example, all we are doing is changing this pointer from this one to this one. So that eventually removes this from the values of this list instance, L instance of a list object. Now, all of this implementation internal to Python, we as a programmer, we don't know how this works, and that's the way of using abstraction to hide it behind the object of list. And that's the whole purpose of defining our own classes and implementing them so that we can make it easier for us to use some compound data types or some objects as part of our implementation. If we try to mess around with the internal implementation of the list class, we would have unexpected results, and they should. The list class should always be interacted with or used with these defined functions that Python language already gives us. So the advantages of object-oriented programming is to bundle all of the data and the behavior inside a class, call it an object, and then use it as one entity wherever we need it in our program. So as I said earlier, it's data and interfaces or behavior or functions that define a specific object. It is a way to divide and conquer our development when we design a solution for a problem. We identify what different kind of entities or objects are present in that overall solution. We design and implement each of them independently and separately. We test them independently and separately, and then we use them in the overall logic of our program. So each of the class that we define as part of our implementation, we can reuse its code. We don't have to change its code once it's complete and it's working. We can define any number of instances for that one object and keep using them in our implementation. All of the functions and the variables that belong to a class, same variable names and function names can be used in any other class or outside of that class in your main global scope, and there is no collision or problem with that. We can also define subclasses of a parent class, and that is a topic that we will cover in detail in next lecture. So there is a difference between creating a class and then using the class. Creating a class means we are implementing it as a programmer. And using an instance of that class would mean that either we or another programmer is creating an instance and then using the interface of that class for some purpose of solving a problem or for some computation. So when we say create the class, that would mean that we give it a class name. We define all of the data attributes that it would contain, and then we would also define the functions or the behavior of that class. And this would become more clear in a few minutes when we look at an example. Using the class, on the other hand, would involve creating a variable or an instance of that class type, and then you doing operations on them by using the functions that we have defined. For example, if we have a list containing two integers 1 and 2, we can interact with it by calling this len function, which would return us the length of the instance, this instance of a list. So let's say for an example, for demonstration in this lecture, we will use the example of a coordinate object. Coordinate is, if you remember, if you have studied mathematics, in a plane, there is in an xy plane. If this is the x coordinate, this is the y coordinate. X-axis and y-axis, we would have some coordinate object sitting here, which would be probably 3 by 4. So if we say we have a coordinate 3, 4, that would be represented by two numbers. First one would be the x number, and second would be the y number. So we will define a coordinate class, and the first reserved or keyword is the word class. That would mean that we are about to define a class. Then we would give it a name, and after that we tell Python what is the parent class of this object. Object is the very basic class, which is the parent of all the classes that we define, unless this coordinate becomes the parent of another class, and then parent of coordinate would be object. That's how this inheritance works in Python. And as I mentioned earlier, we will talk about inheritance in our next lecture in detail. And then inside the class definition, there are attributes or data elements or the behavior of that class. So when we define a function, for example, which does not belong to a class, we use the def class def keyword. Here we are using the class keyword. And then once that's done, then we indent our rest of the code, and which is everything else after that becomes the definition of this new class. So coordinate would be a child or a subclass of object. Object is a class itself, which is the superclass of coordinate. Now, what belongs to a class? There are two things very distinctly. Some are data attributes and some are functions or methods. Data attributes define what represents the class. What is the data representation of the class? It may have 1, 2, or any number of variables containing different values for that object. And methods are procedures or functions that define what this object can do, or how it behaves when we add two of them together, or when we print this instance of an object, what happens in that case. Maybe you can divide two of these objects, and how that division works would be defined as part of the behavior of that class. So in this example of coordinates, let's say we wanted to know how to find a distance between any two coordinates. So if you remember, the distance in a plane, in an XY plane for any two coordinates would be, so this one be x1 comma y1. This is x2 comma y2. The distance between them would be x1 minus x2 squared plus x2 y2 minus y1, or y1 minus y2. Since we are squaring it, it doesn't matter what the sequence is, and taking the square root of both of them. So this kind of calculation Python does not know by default, because this object coordinate that we have defined ourselves, we know it contains a variable x and a variable y. But the distance between any two coordinate objects, we have to define that in a function. So let's take a look at that implementation. So first of all, we define the class. And the first function that we would define is this special function called init, which means whenever we make whenever we define a new variable of this class coordinate, this init function would be called. And the way to initiate or instantiate a variable of coordinate object would be to give it two values of x and y, which would represent where it is present in our xy plane. And all we are doing inside this function is we are saying that this instance is x should be equal to the x that we received from here, and the y within this instance should equate to the y that we received as part of this instance definition. Self would mean that we are now referring to the internal data element of this object, and we would say self dot and then the variable name. So this coordinate object has two variables called x and y, and this initialization function, which is underscore underscore init underscore underscore, we are simply assigning the incoming values of x and incoming value of y to the objects x and y values. So that's how we would define this constructor or initiate init method in Python. So special keyword underscore underscore init underscore underscore self would mean that this is the parameter to itself as an object. When we call this function, we don't have to give this, but when we define any kind of functions within a class, the first parameter should always be self. That would represent itself. And then we have two incoming parameters as part of the definition, which are being assigned to the objects self x and self y data objects. So here's a bit of a usage of this class. We said that, okay, C is a new variable, and its type is coordinate, and the two values of x and y are 3 and 4. So this statement, when we run this, it would create a new coordinate object with the coordinate in that plane values 3 and 4. Okay, somewhere here. And then we define another coordinate object, origin, present right over here at 0, 0. Okay. If we say print c dot x, it would print this number 3. And if we print origin dot x, that would print this number 0. So these 3 and 4, 0 and 0 would become the x and y values of this instance C and origin respectively. When we use this in programming, you'd remember that the first parameter here in the definition of init was self. However, when we use it, when instantiating or calling any function, we don't pass that. And the reason for that is the function which is calling it becomes that self parameter itself. Now let's see what other methods can be defined and what is meant by them. So any class that has a number of functions within it that define its behavior are called its methods. And the first parameter for any function definition within a class is self, which points back to the calling variable um, um, as the reference to who is calling me. For example, in this init, although we did not give self, but self would mean that whichever variable created me, or the C would always point to self. And whenever we call a method or a function for an instance of a class, we always use the dot operator, which means that this X would be the data element belonging to the instance C of coordinate. And if we call a function, which we would see an example in a minute, over there we also use this dot operator so that we can specify that this function that we are calling belongs to this object. So let's define that distance function that I mentioned earlier. The definition of distance would look something like this. The first parameter, as I said, would always be self, so that it can point back to the calling instance. And other is another coordinate object that we are passing it. So we are saying that whichever instance of coordinate asks for a distance between itself and another coordinate object, this is how you calculate it. So x difference square would be self.x minus other.x, as I wrote here. Its own x minus the other x, and squared of that, its own y and the y of the other object, and square that, and then take a square root of the whole thing. So this is how this implementation would look like: the x difference square, y difference square, and then we are returning the sum of those two different difference squares and taking a square root of that. So when we call this distance function, it would give us a numeric distance in this xy plane between any two objects. There are two different ways of calling that function. So we had defined this distance function. There was some code here. The first argument was self, which was the calling instance itself, and second was another instance of the coordinate function. So C is a coordinate object located at x3 and y4. 0 is another coordinate object located at origin, which is x0 and y0. And then we are calling this method distance with C. We are saying that C dot distance and pass it the other coordinate, which is 0. So this would call this function distance. C would become self, and 0 would become other. And this calculation would be done, and an answer will be returned back. Another way of using the same method, but using a slightly different notation, is that we still define C and 0, but we say from the coordinate class, call the function distance, and the first parameter is C, which would become self, and the second parameter is 0, which would become the other. And the same calculation can be done that way as well. Over here, C was the calling function itself, and 0 was this other function. Both of these methods of using the distance function for this class, for any two objects, do exactly the same thing. They're just slightly two different methods of using it. This may look a little bit more explanatory, but this is more intuitive to use when we are doing programming. Now, when we print an object which is not a simple or a scalar or the basic data types that we have seen so far. So here in our code, we have this coordinate object. Let's run these lines so that the class is defined. Now we have the class defined for us. If I try to ask from this example, for example, if I say I have defined a coordinate at 3, 4, and I print C, what happens? Okay. So uncomment this. Let's say we have a coordinate C, and then we are printing the C object. It printed 3, 4 for me. Let's say we have not defined this str function or the print function for this yet. Let's run this once again. I'm not sure if it would remember that from the memory or not. If not, we will just restart the kernel. Okay. So if I print C, which was a coordinate object, it printed something difficult for me to read. It said that C is a coordinate object located at this address in the physical memory of my computer. But if I define this underscore underscore str underscore underscore function, and I'm telling it simply to return this combination of characters, which is angle bracket and then X value converted to string, comma, Y value converted to string, and closing angle bracket. Okay. So what this function does is it implements a special function which would serve the print method for me. So now when I try to print C, which was something like this before, now that I have this underscore underscore str function defined that returns this nicely formatted values of X and Y for my coordinate object, it would return a slightly different representation of this coordinate. So earlier it was a coordinate object at an address in my physical memory, but now after defining this underscore underscore str function, it's saying that C is 3, 4, which was this coordinate object that I defined here. So this is a special method which serves the print function within an object, and there are many other special operators as well that we can define. We can define the add operator with this keyword underscore underscore add underscore underscore. We can also define how to subtract two instances of this object type. We can tell it how to check whether they are equal to each other or not. So in this example, for example, we will say x is x1 plus x2 and y is equal to y1 plus y2, or its own x plus the other x, and its own y plus the other y, and then subtract would be something similar. Equality, we would simply check that self.x is equal to other dot x, and self.y is equal to other dot y. If that's true, then return true, otherwise return false. And we can also define the less than, greater than, the length function, or the string or print function for our objects. For any object in Python, we can ask what its type is, and that would return us the value. For example, if I ask what is the type of C, it would say that it's class coordinate. And if I ask what's the type of coordinate, it's a type, and its parent is object. So that's the basic type. We can also use another special function called isInstance. And this is used to compare two different types, or the type of an object with a specific class name that that we are looking for. And this is sometimes useful in our programming when we are doing some operations. We can check for a type and then do something. Otherwise we don't. So C is instance C, comma coordinate is true, whereas is instance C, comma int is false, which means when I'm checking whether C is a valid variable of type coordinate, Python tells me yes, it is. That's true. If I try to check whether C is a valid instance of the data type int, it says no, it's not. These special functions I've already talked about, we can override or implement a special implementation for all of these operators for our new object, for our class. So second example that we will take a look at today is like this one. We talked about the class coordinate represented by two numbers, which is the x and y values in a xy plane. Let's see how we can implement fractions as a data type or as a class. So internal representation for a fraction is that it has two data elements. One is a numerator and the other is a denominator. For example, 1 divided by 2 is a fraction, numerator and denominator. And then it will have probably all of the mathematical operations as special methods of implementation. We can add to and subtract two fractions. We should also have a function of underscore underscore str underscore underscore that would tell us how to print a fraction. We can probably convert it to float. We should also be able to inverse a fraction, which would just reverse the values of numerator and denominator. So the inverse of 1 by 2 would be 2 or 2 divided by 1. Okay. So let's check out this fraction example in our code. Here's the fraction code. And let's define the class. And if I say a is equal to fraction 1 by 4, a is now defined. B is equal to fraction 3 by 4. So I have two variables, A and B, which are both of type fraction. One is 1 by 4, the other is 3 by 4. If I create another variable called C, which is the sum of A and B, let's run this and see what the value for this is. Okay. So I have said A is equal to fraction 1 by 4, B is equal to fraction 3 by 4, and then C is A plus B. So doing the simple addition of fractions, how we do, since denominator is same, then 3 plus 1, which is 4 divided by 4. So 1 would be the answer. However, it might show it to me slightly differently. If I print C, it's actually 16 by 16. And the reason for that is I have not done the as part of my implementation for addition, I have not done the simplification after the whole calculation of self.numerator times other dot denominator, self plus self.denominator times other than numerator, and then the bottom part of it is just the multiplication of both denominators. So 1 times 4 plus 3 times 4, which is 4 plus 12, 16. And the bottom part is 4 times 4, 16. So you remember we also implemented the float function for this, which is simply returning the division of numerator and denominator. If I call or if I ask for the float value of C, I would get 1.0, which is the division of 16 by 16. What else can we do for this? Let's inverse either A or B for us. So let's say print A dot inverse. Am I passing anything to it? I don't need to, probably. Yeah, it becomes 4 by 1 since it was 1 by 4 before. And if I do inverse of B, that would be 4 by 3. So that's how we define the behavior and the data for a function. We simply have init, we have the print function here, we have the capability to add two fractions, we have the capability to subtract, we have the capability to convert it to a float, and we have the capability or the behavior inside this class to inverse an object of fraction. So this code example is available to all of you. The code file was shared before the class. Let's go back to our slides. So just wrapping up, last couple of slides. The power of object-oriented programming is that we are bundling objects that share a common set of data elements or attributes, things that define them in terms of what they are. And then we also have a set of procedures or functions or methods that define how we can interact with those objects. And those functions would definitely be using the data elements that we have defined for that class. Abstraction is used very heavily here, the concept of abstraction. The implementation of these objects, for example, we have just seen what kind of we know when we define a coordinate object, we give it two numbers. One is the x value and one is the y value. And then we simply call some functions on it. We call the function to find the distance. As the second programmer who is using the coordinate class to instantiate or create an object of coordinate type does not need to know how the distance was calculated, but he can simply call that function of distance. For the fraction, we implemented the addition, subtraction, multiplication functions, for example. And we have defined a fraction with a numerator and denominator. One programmer would have implemented that class, but the other programmer does not need to know how two fractions are added together. He can simply call that add operator and use it. So that's how abstraction works. These are very simple examples, but for complex classes, this is the concept of abstraction, that the implementer would know how the function implementation is done, but the other users of that class would simply just call the functions and use it. They don't need to know the internal details of the implementation. That would mean by the abstraction. And these are the layers of abstraction that we use. When we talk about inheritance in the next lecture, you would see that there are multiple levels of or layers of abstraction between objects when there is a family tree of multiple levels of child classes. And all of the behavior and data for the parent class are inherited by the child class. And then all of that plus the previous ones are inherited by a child of that child class. So that kind of multiple levels or layers of abstraction make the design much more powerful. And we can create any number of classes of objects on top of previously defined classes as their parent classes as much as we want, and continue to use the power of object-oriented programming as part of our design. So that would be the end of the lecture today. In the next class, we would explore this further by talking about inheritance between classes and how a parent-child relationship works for a class, and how that results in a child class using the functionality and data of its parent class. That would be all for today. Thanks, everyone. Bye.